Hello Tade, we are going to learn 3D graphics. In Module 3 we have these topics: 3D coordinate systems and transformation spondy, orthographic and perspective shading, flat, Goro and Phong shading, hidden surface removal texture mapping. In computer graphics, a 3D coordinate system is used to represent points and objects in three-dimensional space. The system typically uses a right-handed coordinate system where the x, y, and z-axes are oriented in specific directions. Transformations are used to manipulate 3D objects. In the coordinate system, the three main types of transformations are translation, rotation, and scaling. 1. Translation. Translation moves an object in a specific direction and distance along the x, y, and z-axes. It involves adding a constant offset to each coordinate of the object. 2. Rotation. Rotation rotates an object around a specific axis by a given angle. It can be done in different ways, such as Euler angles, axis angle representation, and quaternion rotation. 3. Scaling. Scaling changes the size of an object along the x, y, and z-axes. It can be uniform or non-uniform, and involves multiplying each coordinate of the object by a scaling factor. These transformations can be combined to create more complex transformations, such as skewing, shearing, and perspective projection. In addition to transformations, the 3D coordinate system also includes concepts such as the viewing frustum, which is a pyramid-shaped volume that defines what part of the 3D scene is visible from a particular viewpoint. The frustum is used in techniques such as perspective projection to create the illusion of depth and distance in a 3D scene. Understanding 3D coordinate systems and transformations is essential in 3D graphics programming, as they allow programmers to create and manipulate complex 3D scenes and objects. They are used in a variety of applications, such as video games, virtual reality, architectural visualization, and scientific simulations. Projection is the process of transforming a 3D scene into a 2D image in computer graphics. There are two main types of projections used: orthographic projection and perspective projection. 1. Orthographic projection. In orthographic projection, objects are projected onto a flat plane without taking into account the distance between the objects and the plane. This means that all lines parallel to the viewing plane are projected as parallel lines in the 2D image. Orthographic projection is commonly used in technical drawings where accurate representations of objects are required. 2. Perspective projection. In perspective projection, objects are projected onto a flat plane as they would appear to the viewer from a specific viewpoint. This means that objects that are farther away from the viewer appear smaller in the image than objects that are closer. Perspective projection. Projection is commonly used in 3D graphics applications to create the illusion of depth and distance. Perspective projection can be achieved using a variety of techniques, such as the pinhole camera model, which models the projection process as if the scene were viewed through a small hole in a flat surface. Other techniques include the use of camera parameters such as the field of view, the aspect ratio, and the near and far clipping planes to control the projection. Understanding orthographic and perspective projection is important in 3D graphics programming, as it allows programmers to create realistic and accurate images of 3D scenes. Perspective projection is particularly important for creating immersive experiences in applications such as video games, and distance is essential for creating a believable virtual environment. 3. Phong shading. Phong shading is a more complex shading technique that calculates the color of each pixel in the scene based on the lighting and the surface properties of the object. It takes into account the ambient, diffuse, and specular lighting components, as well as the material properties of the object, such as its shininess and reflectivity. This produces a highly realistic image with accurate shading and highlights. Each shading technique has its own advantages and disadvantages. Flat shading is fast and simple, but produces a less realistic image. Goro shading produces a more realistic image, but can have visible artifacts at the edges of polygons. Phong shading produces the most realistic image, but can be computationally expensive and may require a high-end graphics card. Understanding the different shading techniques is important in 3D graphics programming, as it allows programmers to choose the appropriate shading technique for their application and create realistic images of 3D objects. Hidden surface removal is the process of determining which surfaces in a 3D scene are not visible to the viewer and should therefore be removed from the final rendered image. This process is important because it helps to create a more realistic and accurate representation of the scene by preventing objects that are hidden behind other objects from being visible. There are several techniques used for hidden surface removal. -1-to-1 backface culling. This technique involves removing polygons that face away from the viewer. It assumes that any polygons facing away from the viewer will not be visible and can therefore be discarded. 2. Z-buffering. This technique involves using a depth buffer, or Z-buffer, to keep track of the distance to each pixel on the screen as each polygon is rendered. Its depth value is compared to the depth value stored in the Z-buffer for each pixel it covers. The polygon is closer to the viewer than the current depth value. It is rendered and the Z-buffer is updated. 3. Occlusion culling. This technique involves identifying objects or parts of objects that are completely hidden from the viewer and removing them from the scene. This can be done using various algorithms, such as Bufrasum culling or portal culling. 4. BSP trees, binary space partitioning. BSP trees are a data structure used to represent a scene as a hierarchy of nodes, with each node representing a partition of the scene. By traversing the tree and testing which partitions are visible from the viewer, hidden surfaces can be removed from the scene. Each technique has its own advantages and disadvantages, and the choice of which technique to use depends on the specific requirements of the application. Understanding the various hidden surface removal techniques is important in 3D graphics programming, as it helps programmers to create more realistic and accurate images of 3D scenes. Texture mapping is a technique used in computer graphics to add detail and complexity to 3D objects. It involves mapping a 2D image or texture onto the surface of a 3D object to create the appearance of surface detail, such as bumps, scratches, or patterns. Texture mapping works by dividing the surface of the 3D object into small polygons and mapping a 2D texture onto each polygon. This is done by assigning texture coordinates to each vertex of the polygon, which define how the texture is mapped onto the surface. The texture coordinates are usually defined as a pair of u and v values, which correspond to the x and y axes of the texture image. Once the texture coordinates are assigned to each vertex, the texture can be mapped onto the surface of the object using a process called interpolation. This involves calculating the texture color for each pixel in the polygon by interpolation. This involves calculating the texture color for each pixel in the polygon by interpolating between the texture coordinates of the vertices. Once the texture coordinates are assigned to each vertex, the texture can be mapped onto the surface of the object using a process called interpolation. This involves calculating the texture color for each pixel in the polygon by interpolating between the texture coordinates of the vertices. Texture mapping can be used to create a wide range of effects, from simple patterns and designs to complex, realistic textures such as skin, wood grain, or metal. It is often used in 3D computer games and animation, as well as in architectural visualization. product design, and other applications. Some common types of texture mapping techniques include 1. Planar mapping. This involves projecting the texture onto the surface of the object from a single direction, such as from above or below. 2. Cylindrical mapping. This involves wrapping the texture around the surface of a cylinder and then projecting it onto the surface of the object. 3. Spherical mapping. This involves projecting the texture onto the surface of a sphere and then wrapping it around the surface of the object. 4. UV mapping. This involves manually assigning texture coordinates to each vertex of the polygon, allowing for precise control over how the texture is mapped onto the surface. Texture mapping is a powerful tool for creating realistic and detailed 3D graphics, and is an essential part of modern computer graphics technology. Thank you for watching us. Stay tuned for next part.